Session 9 of the FDP brings us an enriching interaction with Mr. Parvinder Singh, who is currently serving as Assistant General Manager and Head of Department in Mechanical Engineering and Projects at Century Plyboards India Ltd, Hoshiarpur.
Good evening, everyone.
With
First
us
of all, I
from
thank the management and organizers for giving me the opportunity to interact with you today. My name is Parvinder Singh, and I am currently working as Deputy General Manager at Mechanical Department at Century Plyboard Limited, Hoshiarpur. I have a total industrial experience of 25 years, and my professional journey started at Rupana Paper Mill, where I worked for 5 years and learned the fundamentals of heavy mechanical systems. After that, I worked at Quanta Paper for 4 years, then Shreyans Industries for 13 years. And for the last 3 years, I have been working with Century Plyboard Limited. I have completed my BTech in mechanical engineering, and later I pursued an MBA in operation management, which helped me understand not only machines but also systems, cost, efficiency, and people. So today, whether I share with you will be practical, experience-based knowledge, not just theory. Here we go with higher alcohols as alternative fuels. Here is the scope and coverage. Methanol C1. Second one is ethanol C2. Third one is propanol C3. Fourth one is butanol C4. And last one is pentanol C5. There are some agenda and learning objectives, such as motivation, decarbonization, air quality, energy security. Other one is fuel property, fundamentals, and comparisons. SI and CI combustion mechanism and performance. Emission standards, infrastructure, and safety. Last is techno-economics, case studies, and future outlooks. So why alcohol fuels now? Climate target, renewable fuel, mandates, accelerating global. There is one graph also showing on screens. You can see that drop in and flex fuel pathways allow near-term impact without fuel electrification. Another one is high octane and oxygen content enable significant engine and efficiency gains also. Emerging e-fuels power to alcohol closes carbon loop effectively. What is higher alcohols? Classification of alcohols are alcohols by carbon number C1 minus C5 positive from methanol to pentanols and higher. Core focus is methanol. There is one formula mentioned in screen, MEOH and ethanol ETOH. Other one is propanol, butanol and pentanols. Distinct traits, polarity, oxygen contact, and hydrogen bonding distinguish them from hydrocarbons. Relevance is key enabler for acid blending, CI dual fuel, marine, and racing applications. There is another graph showing on screen of core fuel properties at a glance. What is volatility and distillation behavior? One graph is also showing on screens. You can see that vapor pressure and boiling points shift significantly with carbon chain length. Azeotrophs form with hydrocarbons causing non-ideal boiling behavior, for example, E10. Implications, critical impact on cold start, vapor lock, and evaporative emissions. Last is blending. E10 versus E85 requires distinct RVP grades to manage seasonal volatility. Miscibility, hygroscopicity, and water tolerance. One picture is shown on your screens. One is lower alcohols, C1 to C2. It is highly polar nature, strong affinity for water, resist mixing with non-polar hydrocarbons. Second is high hygroscopicity, rapidly absorbs moisture from ambient air during storage. Last is phase separation risk. Separate into aqueous organic layers if water threshold exceeded. Another picture is of higher alcohols, which is C4 above. Am- Amphiphilic properties. Longer carbon chain acts like hydrocarbon, good miscibility. Hydrophobic behavior. Resist water uptake. For more stable in humid environments. Last is co-solvent capability. That is stabilize ethanol, gasoline, blends, preventing and separation also. Material compatibility and corrosion. There is 4 points of that. First one is elastomers and plastics. It is swelling and abritlement risks. Metal, they are aluminium, zinc, and copper corrosion with low pH. Conductivity with galvanic effect in presence of water. Last is mitigation. Compatibility materials, inhibitors, and coatings. What is safety and handling? There are also 4 points of that. First is flammability limits and flash point vary. Methanol risks include invisible daylight flames. Second is vapor density and toxicity, mandate dedicated ventilation and gas detection system. Third one is firefighting requires alcohol resistance, which formula is AR into AR equals to A triple F. Form standard hydrocarbon form degrade. Last is strict transport regulation for chemical labeling, spill containment, and PPB compliance. What is environmental context? Tailpipe, lower PM soot potential aldehydes increase. Second is WTW, GHG. Here is that heavily dependent on feedstock and process energy. Third is air toxics, required specific dilution and catalyzed strategies. Last one is circulatory. Bioroutes and power to alcohol, e-fuels closes the loop. Here is one diagram shown on your screens. You can see that, which is of SI combustion fundamentals with alcohols. Let's discuss about diagram. High octane, which is RON smaller than 100, suppresses smoke, enabling higher compression ratios and optimal spark timing, which formalize MBT. Second is charge cooling via high latent heat, increases air density formula VE and drastically reduces end gas temperatures. Last is tolerance for lean operation, which improves thermal efficiency due to wider flammability limits. Here is one another diagram on your screens, which is of laminar flame speed versus equivalence ratio. Higher laminar flame speeds, MEOH and ETOH, exhibit significantly faster flame propagation than gasoline, especially in rich mixture. Second is shortened burn duration. Faster turbulent compression allows MBT spark timer closer to TDC, improving thermal efficiency. Last is operational implications. Benefits includes higher indicated efficiency, but create a risk for cold start misfires due to vaporization issues. What is assay emission formation with alcohols? There are 4 points of that. First is of COHC. Trends are highly sensitive to lambda and wall wetting effects due to high latent heat. Second one is unregulated aldehydes, forma, which have two more parts, which is formaldehydes and etc. halide, may increase requiring specific oxidation catalysis. Third one is NOx is generally low due to charge cooling reducing peak temperatures through calibration dependent. Last is catalyzed light off challenges arise from cooler exhaust. Oxygen storage capacity, which short form is OSC, interacts with fuel oxygen. One diagram is of ambient temperature shown on your screen. High latent heat significantly hinders cold vaporization, which formula is MEOH, smaller than ETOH. Sorry, bigger than ETOH. Second one is mitigation. High enrichment, retarded spark timing, heated injectors, or secondary gasoline start. Startability improves with higher alcohol chain length, butanol outperforms ethanol. Extreme cold, above minus 10 degree, often requires seasonal RVP adjustments or E70 winter grades. CI combustion's fundamentals and challenges. There is diagram which represents low cation number alcohols 3 minus 5 versus diesel 45 minus 55 cause resistance to auto auto ignition and cold start issues. Extended ignition delay, longer mixture time leads to larger accumulated pre-mixed fuel fraction before ignition. Rapid pre-mixed burn, resulting combustion is faster and more intense, risking high pressure rise rates, which is ringing. Last is strategy required. Must use pilot injection, dual fuel, or ignition improver, ED95 to force ignition. You can see a diagram also of crack angle. Alcohol in CI, ignition and injection strategies. Diesel pilot with prot injected alcohol dual fuel allows reliable ignition of low cation alcohol. Direct injected alcohol typical requires glow plugs or ignition assist hardware. Less common. Ignition improves. Example nitrates are necessary for single fuel blends to restore stain number. Multiple injections are used to temper the high pressure rise rate typically of rapid alcohol combustion. There is diagram of soot suppression mechanism. You can see that NOx minus PM2 trade-offs with alcohol strategies. Dual fuel soot PM drops significantly due to oxygen rate. NOx varies with pilot timing and EGR. Second is RCCI-LTC. Proper, proper stratification enables ultra-low NOx and PM simultaneously, breaking the trade-off. Third is constraints. Operating limits are often defined by pressure, rise rate, noise, and combustion stability. Result, alcohol shift the Pareto frontier closer to the region zero emission. You can see the diagram of NOx versus soot trade-off comparison on your screens. There is another diagram of operating range extension HCCI load limits. High octane enabler equals to higher RON of alcohol suppresses rapid auto ignition, allowing HCCI operation at higher compression ratios using standard SI like hardware. Second is thermal management. High latent heat permits aggressive intake, charge heating strategies to precisely control auto ignition time. Load extension. Alcohol fuel broaden the stable HCCI operating window, which formula is IMEP by 30 to 50% compared to gasoline. You can see the diagram. Let's talk about measuring alcohol combustion. In cylinder pressure, HRR, NOC, and PRR metrics. Second is optical methods, which are PLIF for formaldehyde, OH soot, exhaust analyzers for aldehydes and unregulated species. Last is data needs, repeatability across blends and temperatures. What is SI hardware and calibration adaptation? There are 4 points of that. First one is flex fuel sensors and closed loop lambda control. Second is larger injectors pump for lower LHV fuels. Third one is compression ratio and boosting opportunities. Let's talk about last point. No control. Ion sense pressure based strategies. Let's talk about CI hardware and system consideration. It also has 4 points. First one is injector material and seals must be compatible with polar alcohols. For example, FKM, stainless steel. Second one is pilot and multiple injections capabilities required for precise ignition and heat release control. Third point is intake port injection. It's enable cost-effective dual fuel retrofits for existing engine. Last one is turbocharge and EGR, turning necessary to manage altered exhaust enthalpy and thermal profiles. Lubricity, wear, and oil management. Let's talk about that. It also has 4 points. First one is alcohols reduce fuel lubricity, increasing wear risk of high pressure pumps and injectors. Oil dilution occurs from low vitality, fuel fraction, and cold start potential, thinning the lubricant. Third point is combustion byproducts can accelerate total waste number, which short form is TBN, depletion and corrosion. Last is mitigation, which prescribed use lubricity additives, adjust oil changes interval, and optimize warm-up strategy. After treatment interaction, it has total 5 points. Let's talk about first one. TWC challenges, oxygenate, rich exhaust, and altered light of behavior. Second is CI oxidation, which we also call DOC. Critical for aldehyde conversion efficiency. Third one is particular filters, DPF. Lower soot load reduces regeneration frequency. Third is SCR dynamics. NOx conversion rates vary with lower exhaust temperatures. And let's talk about our last point, durability risks, which is potential catalyst, poisoning, and sulfur sensitivity. Calibration strategies for performance and efficiency. Spark time optimized to MBT, leveraging increased knock margin, which symbol is SI. Second is lambda or EGR. Sweeps to define best trade-off for BSFC and emission. Third is boost and compression optimization, exploiting high RON, MON values. Last one is CI, pressure rise rate, PRR management via injection, timing, and fraction. Let's talk about blending strategy, which is low, mid, and high level SI blends, which vary from E10 to E85. Advanced CI formulations and emulsions, dual fuel and RCCI concepts. Let's talk about low level blends, which is E10 to E30, BU8 to BU16. Generally compatible with existing fleets. RON boost and mild charge cooling benefits, emissions PM down, aldehydes manageable. Last is infrastructure, minimal changes, verify material. There is two figures shown on your screen. Let's talk about first one, which is of performance opportunities. It has total 3 points. High knock resistance, High RON allows increased compression ratio and optimized spark advance. Second is charge cooling effect. High latent heat cools intake air, increasing density and volumetric efficiency. Last is emission reduction. Oxygenated fuel significantly reduces PM-soot and co emissions. Let's talk about another figure, which is of system requirements. It also has 3 points. First one is material compatibility. Requires FFV, spec, elastomers, and corrosion resistant fuel system components. Second one is of fuel system sizing, which is lower LHV, necessitates 30 to 50 percentage larger injectors and pumps for same range. Last one is cold start strategy, which requires seasonal RVP adjustment, E70 in winter or intake heating. It is hardware upgrade, and the first one is efficiency gain. It is difference between two figures. Which one is performance opportunities and system requirements. Butanol and higher alcohol blends. Higher energy density and lower vapor pressure than ethanol offer improved fuel economy and handling, better miscibility and hydrocarbons, and less hygroscopic, reducing phase separation risk. Third is significant octane uplift with lower impact on evaporative emission compared to lower alcohols. Standardization is rapidly evolving. ASTM D7862 with ongoing pilot deployments in fleets. You can also see the key takeaway mentioned at the bottom of the screen. Let's talk about alcohol diesel blending strategy. It is described in 4 points. Direct blending limited by phase separation. Co-solvents, example, biodiesel, higher alcohols are required. Microemulsions using surfactants enable stable blends despite water content. Chain improvers, example, nitrates, essential to restore auto-ignition quality. Critical challenges, water tolerance, stability, and low temperature operability. You can see the key takeaway. Let's talk about dual fuel CIN RCCI concepts. It is in 4 steps. First is port injector, intake stock, port injection of low reactivity fuel. Then compression, formulation of homogeneous background charge. Then we have ignition trigger, direct injection of high reactivity fuel. Last one is combustion, stacked heat release via reactivity stratification. Emissions, which is of overview and matrix. Regulated NOx, CO, HC, PM mass, and PN particles. Unregulated aldehydes, ketones, PAHs, ammonia, and 2O. Matrix specific emissions. Distance. Methods severe sampling, condensation particle count. You can see the bar graph showing on your screen. Let's talk about that. First, we have NOx reduction, which represents high latent heat cools the intake charge, reducing peak combustion temperatures and thermal NOx formation. Second is co-decrease, which represents fuel-bound oxygen improves local oxidation efficiency, significantly lowering co-emission across most loads. HC complexity, while oxygen rate, aid combustion, poor vaporization, wall wetting in cold conditions can spike engine out. HC. Last one is CI context, which describe dual fuel strategies, often break the knock suit trade-off but may require dogs to manage light load HC slip. You can see the bar graph. Aldehydes and unregulated species describes in 4 points. Let's talk about first one. Formaldehyde, acetaldehyde formation pathways driven by partial oxidation. Second is mitigation relief. Mitigation relies on effective oxidation, catalysis, and precise calibration. Third one is measurement challenges include sampling line losses and chemical artifacts. Rising health concerns are driving new regulatory monitoring trends. See the key takeaway at the bottom of your screens. See one diagram on your screens of particle number versus engine load, which is represented in line graph. Let's talk about that. Significant PM soot mass reduction in SI and CI engines due to fuel-bound oxygen inhibited precursor formation. Second is nucleation mode. Ultrafine particles may increase under cold or lean conditions. Reduced soot loading extends DPPF or GPF regeneration intervals and durabilities. Last one is PN limit. Euro CD or -7 requires optimized injection strategies, even with clean alcohol fuel. You can see the key takeaway also. Let's move to another point. Tailpipe versus well to wheel emission. There are total 4 steps of that. First one is feedstock, which includes farming, land use, and harvesting. Then production, which includes refining, synthesis, fermentation. Then move to distribution, transport, storage, and dispensing. Last, we have vehicle use, combustion, tailpipe exhaust. You can see the diagram mentioned on your screens. Then we have topic of fuel handling and infrastructure. It includes three it includes 3 points, which includes a lot of topics. First one is material storage and logistics compatibility. Then phase separation and water management. Last, evaporative emission and vapor load. Let's move to another slide. Here we have topic about compatibility in storage and distribution. First, we have tanks and liners. It described specific compatibility required for steel, aluminium, and fiberglass to prevent degradation. Then, seals and gaskets. FKM, Whiten, and PTFE are preferred. Avoid NBR nitrate for high alcohol blends. Pump and dispenser upgrades. Retrofitting hardware and updating labeling requires for consumer safety. You can also see key takeaway, which is select alcohol compatible materials across the supply chain to prevent failures. Then we have volatility, vapor flow, and permeation. RVP tuning and seasonal volatility grades are critical to balance cold start against vapor flow issues. Second is permeation through polymers increases with alcohol blends, risking canister overloading and evaporating emission. Then we have engine bay heat soak requires robust hot restart strategy to prevent fuel vaporization in the rail. Let's talk about key takeaway, which is control volatility and permeation to maintain drivability and emissions compliance. Safety systems and transport. First, we have gas detection and ventilation in storage garages, which described crucial for mitigating vapor accumulation given specific density and flammability limits. Then fire suppression. AR in AR to AFFF forms and compatibility, which is standard forms, degrade rapidly. Alcohol resistance, short form AR, forms are mandatory. DOT or ADR transport classes, placarding, and training. Specific protocols for toxicity, methanol versus journal flammable liquid handling. Let's read about its key takeaway. Safety planning must reflect polar solvent behavior and response protocol. Then we have standards and sustainability. We have their topics are fuel specification and test methods, then sustainability and WTW framework. Techno-economics and case studies are also mentioned here. Let's talk about fuel specification and test methods. First, we have ASTM D4806 base component, which prescribed standard specification for denatured fuel ethanol for blending with gasolines for use as automotive spark ignition engine fuel. Then we have ASTM D5798 finished fuel, which is standard specification for ethanol fuel blends, which varies from ED75 to ED85 for automotive spark ignition engine, which is flex fuel. Then EN15376 base component, automotive fuels, ethanol as blending component for petrol to requirement and test method, which is European standard. Last we have ISO 22854 test method. Liquid petroleum products, which are determination of hydrocarbon types and oxygen rate in automotive motor gasoline. Why it matters? Quality insurance, which includes prevents engine damage by controlling water, acidity, and gums. Then legal compliance, meeting specs is mandatory for retail sale and warranty coverage. Interoperability ensures fuel work across diverse OEM hardware globally. It also have one warning. Always verify the latest revision. For example, D480621 before procurement. Let's talk about key takeaway. Conformance to ASTM-EN-ISO specs underpins safe, consistent blending and vehicle operation. Methanol and butanol standards landscape. First, we have ASTM D5797 fuel methanol M85 standard specification for fuel methanol, which varies from M70 to M85 for automotive spark ignition engine, which is similar to E85 but for MEOH only. Then we have ASTM D7862 butanol blend, which describes standard specification for butanol for blending with gasoline for use as automotive spark ignition engine fuel, which vary up to 12.5% volume. Then we have regional and emerging pilots, evolving specs for higher alcohols, which is C plus positive, and regional methanol standards. For example, China M100, India BIS M15 M85. What is market status of that? Methanol maturity, high blend specs M85 or M100 are established in China. US D5797 exists, but market uptake is lower than butanol drop in. D7862 allows butanol use in standard gasoline infrastructure without FFB hardware. In many cases, material caution spec compliance doesn't guarantee material compatibility in legacy vehicles. Check Alstromer data. It also has one warning. Standards evolve rapidly with e-fuel innovation. Always verify the current revision year before contracting fuel supplies. Let's see the key takeaway, which is very important for reminder. Methanol and butanol have defined or emerging specs. Due diligence on update is essential. Policy drivers and market signals. These are US RFS and California LCFS credits incentivize carbon intensity reduction. Then we have EU priority, mandatory renewable targets and strict sustainability criteria. Indian roadmap, E20 mandates and procurement policy driven adoption. Then last we have corporate goals. Net zero commitments shaping private fleet fuel demand. Key takeaway, it shows us that policy frameworks materially influence the business case for alcohol fuels. Let's move to another slide. Here we have sustainability and WTW assessment. First, we have feedstock range from starch or sugar crops to cellulosic residues and industrial off gas. Then, allocation methods, energy mass displacement, critically define carbon intensity scores. Then we have indirect land use change, which short form is ILUC, and biodiversity risks remain key regulatory constraints. Last, we have certification schemes. Examples RSB, ISEC, are essential to verify supply chain sustainability. Its key takeaways: robust, well to wheel accounting and certification are prerequisites for credibility and policy credits. Here we have some steps of production pathways, bio and e-fuels. Let's talk about biochemical route. First, biomass feedstock, starch, sugar, cellulose, converts into fermentation, yeast, ABE process, engineered microbes. Then we have bioalcohols, ethanol, butanol, propanol, which varies from C3 to C5. Second, we have thermochemical route. We have to take waste MSW would be biomass industrial of gases to gasification, which sees production CO plus H2. Then it moves to synthesis methanol mixed alcohols. Then we have power to X route. It started with renewables, electrolysis plus captured CO2. Then catalytic synthesis, methanol synthesis loop. Then we have in the form of result e-methanol, carbon neutral liquid fuel. Its key co-products are DDGS feeds, acetone, heat oxygen. Let's move to another slide. What are techno economics and cost drivers? Feedstock cost and availability dominate OPEX, often accounting for 60 to 80% of total production costs. Another we have capital intensity varies significantly. Biological fermentation is generally lower capex than thermochemical or e-fuel routes. Then we have carbon intensity premiums, which is LCFS credits, and policy support mechanism are critical determinants of profitability. Last we have scale, process, integration, and valorization of co-products. For example, DDGS chemicals are essential to improve margins. Let's talk about its key takeaway. Competitive levelized cost of fuel, which short form is LCOF, hangs on secure, low cost feedstock or power and robust carbon policy mechanisms. You can see the case study of Brazil, ethanol, and flex fuel. First, we have deployment context. You can see the diagram, which represents three dots of green colors. Since the 1970s, protocol program Brazil has integrated sugarcane ethanol into its national energy matrix, mandating blend levels and pioneering flex fuel vehicles, which short form is FFVS. E27 mandatory blend and 85% positive FFV sales share. Let's talk about its key technical and market insights. We have total three. First one is hardware adaptation. Production FFVs use upgraded fuel pumps, injectors, and corrosion resistant materials, which are coated steel or plastic. To handle any mix from E27 to E100. Second, we have consumer behavior. which is very important. Drivers switch fuels based on the 70% price partially parity rule, energy content ratio. The market is highly price elastic, demanding robust engine calibration for transient switching. Last, we have environmental impact. Significant reduction in fleet-wide CO2 sugarcane ethanol has high energy return on investment, which short form is EROI, and low life cycle carbon intensity. Let's talk about its key takeaway. Brazil demonstrate that durable national scale ethanol deployment is feasible with policy consistency and FDP tech. Just give me 2 minutes, guys. Then we have case study of methanol in marine and heavy duty. Deployment context. You can see the diagram. Methanol. You can also read the formula of methanol, which is MEOH, is rapidly emerging as a leading alternative fuel for the global shipping industry to meet IMO 2030 or 2050 decarbonization targets. We also have IMO Tier 3 NOx compliance, 10 to 15% CO2 reduction, gray methanol. These operation and technical findings are dual fuel engine technology, which described large two-stroke and four-stroke engines utilize a diesel pilot injection to ignite methanol. This dual fuel approach ensures reliability and redundancy if a methanol supply is interrupted. Storage and bunkering. Methanol is liquid at ambient temperature, making it far easier and cheaper to store than LNG or hydrogen. It requires double-walled pipes and specific ventilation due to toxicity. Then we have heavy-duty truck pilots demonstration in China and Europe show methanol trucks achieving parity in torque power with diesel, offering a lower TCO route compared to full electrification in long haul sectors. Its key takeaway are methanol is gaining significant traction in marine and heavy duty sectors due to liquid handling advantage and proven dual fuel tech engine tech. Let's move to the another slide. So guys, this is your session. Thank you everyone.
Thank you so much, sir. A heartfelt thanks to sir for such an engaging and informative session. We truly appreciate the time you shared and the knowledge you imparted us. Thank you so much, sir.
Thank you, ma'am.